Hey everyone, welcome to our presentation. Today my teammates and I will be discussing our midterm project for our deep learning class. If you'd like to follow our project process through our blogs, please feel free to check out the link below. So before we get started, we're going to give a brief introduction to our team. We're all data science master students at Brown. My name is Cameron.
I'm Chris.
Hey guys, I'm Jillian.
Great, let's get started. This project involved a 5-class multi-classification problem posted as a Kaggle competition. The main driver of this competition was to create an image classification tool that can predict whether or not a cassava plant has a particular disease based off images of the plant's leaves. This is a really important topic considering cassava is a staple crop for many households in sub-Saharan Africa, and crop yields are often destroyed by disease. So an inexpensive way to detect disease in plants would be a great benefit to those who can produce the plants in the region. And with that, I'm going to turn over the exploratory data analysis to Jillian.
Hey guys, it's Jillian. So EDA is an important part of the data science pipeline because it gives us the opportunity to analyze and investigate the data set. By doing so, we can better understand the data and any outliers or errors. As Cameron mentioned, we have 5 classes of images. On the left, we can see 5 example images of each class, from CBB on top to healthy example on bottom. Not sure about you, but it was hard for us to decipher which plant is which. On the right is a breakdown of the images of our dataset by the 5 classes. As clearly displayed, the dataset is disproportionate in favor of CMD. This is something that is necessary to consider when training a model. And now I'll hand it over to Chris.
All right, Chris here. In the beginning stage of our project, we implemented an instance of the LeNet 5 architecture as our baseline. While this ultimately proved to be much, much smaller than the final models we ended up using, this is a widely used standard in the image recognition literature, so we decided to use it as an example of a simple baseline CNN for our task. Now moving on to data augmentation. Before we go into detail about our models, we'll tell you a little bit more about the data augmentation process and a couple of key technical hurdles we encountered through the project. So as is the case with any largely data-intensive machine learning project, data augmentation is a core strategy in bolstering our training set to make our models more generalizable. Data augmentation does this by adding copies of training samples to the data set with certain image transformations applied to them. This mimics the effect of having a larger data set from the beginning. After we inspected the training images, we decided that it would be useful to apply random horizontal and vertical flipping, random rotation, random translation, and random changes in image contrast. And now Jillian will walk you through our RAM issues during the project.
Great, Jillian again. So one of the biggest challenges and time warps we had in this project was RAM. The standard version of Google Colab only allocates about 13 gigabytes of RAM. Since we were using large models, this wasn't enough and resulted in us getting stuck on the first epoch of training. To fix this problem, we investigated the impact of changing the input size of our training images, adjusting our batch size, and changing the location of our data augmentation. Originally, our data augmentation strategy was to implement in the sequential model, but applying it directly to the training set by using the map function allowed us to avoid reclassifying images, thus saving space. These updates, along with upgrading to Google Pro, allowed us to run our models before running out of RAM. Now I'll hand it over to Cameron.
Cameron here. So we extracted our data for training and validation from TF record files rather than directories of JPEGs. The main reason for this was time improvements, since TF records is a binary file format specifically optimized for integration with TensorFlow pipelines. To use this file format, we built several image parsing functions from scratch that map the files to TensorFlow datasets. And with this, I'm going to turn it over to Chris to talk about improvements and attempted improvements upon our original models through our blog post.
All right, Chris here again. While Cameron brings us to the next section, we're going to talk about improvements we made to our previous iteration of our transfer learning models. So we found the best results after setting our training procedure to run for a maximum of 100 epochs, and we settled on using a batch size of 16 and an initial learning rate of 0.001. As for data augmentation, we adjusted our approach to transform our input images using all of the transformations we discussed earlier, as well as applying a central crop to each image, which cut out the center 360 by 360 pixel section of the original 600 by 800 sample. This helped both by isolating the most important part of the image, usually found in the center of the photos, and reducing image size, which considerably reduced training time later on. We'll come back to ensembling later on when we talk about our final model, but a feature we attempted and didn't end up using was the application of different learning rates to the different sections of our model. Because we were building models using transfer learning, it's a common approach to train a model with a small learning rate being applied to the pre-trained layers and a large learning rate applied to the new layers that are added on at the top of the model. This is called fine-tuning, and we tried to implement it using a multi-optimizer object that paired the two sections of our network with their own learning rates. However, this caused our validation loss to plateau fairly early on in training, and we ultimately found better results from just applying the same learning rate to the entire model. Another thing we tried but didn't end up incorporating into our final model was the use of class weighting. As we saw from our EDA, our training data is incredibly skewed towards one class over the others. When we saw this, we weren't sure if this would end up reflecting the class distribution of the test data that our model would see later on. So to find out the class distribution of the test data, we implemented 5 different naive classifiers, each predicting a single fixed class for all inputs, and fed those to Kaggle as 5 separate submissions. These classifiers' accuracies ended up showing us that the test data had roughly the same distribution as our training data, so we knew we wouldn't have to weight the training samples in any special way to compensate. While we were training different model architectures and trying out different training procedures, we noticed that while it's a common practice to freeze the layers from a pre-trained model and only change the weights in the additional top layers, this led to our model reaching a peak validation accuracy only in the neighborhood of around 60%. So we decided to train all layers, including those from the base network. As for the structure of the layers we added on top of the pre-trained networks, we initially tried using 5 or 6 dense layers to gradually reduce the dimension from our base model output down to our 5 output classes, but this ended up being far less effective than just having 2 dense layers lead from our base model to our softmax output. This leads us to believe that our base model's pre-trained weights encoded some feature detectors that were already fairly good at detecting relevant Cassava leaf features and ultimately didn't require that much adjustment. Now, Jillian will give you more detail about what transfer learning is.
Hey guys, it's Jillian. So by now you've heard the term transfer learning quite a few times, so we want to discuss what exactly that means. The idea of a transfer learning model is to build a model architecture by using a pre-trained model with the ability to add a section of layers. Transfer learning models are powerful and computationally inexpensive since we're instantiating a model with weights achieved by training on a given dataset, in our case, ImageNet. This method is often faster, more accurate, and requires less training data. Originally in our project, we froze the layers in the transfer learning model because ideally we wouldn't have to retrain those layers. Since then, we have decided to unfreeze the layers since the pre-trained weights were not performing well enough. There are many different commonly used computer vision architectures that each have their own pros and cons. After researching different options and reviewing what we have learned in class thus far, we decided to use ResNet 50, Inceptionnet, and Efficientnet. Now we will go into further detail about each, starting with Chris, who will talk about ResNet 50.
All right, Chris again. So the first transfer learning model we implemented used ResNet 50 as a pre-trained base model. ResNet 50 is a standard in the world of computer vision models, and it's defined by its use of residual connections. As you can see by this figure here, residual connections are a very simple idea that enable a layer block to have its input added to its output as a way of eliminating the need for the layers in that block to relearn any information that's already given in its input. These residual connections make ResNet so powerful because their increased expressivity makes their training very stable, even with such a large number of layers. In our ResNet model here, we ended up having just over 24.5 million trainable parameters, and we were able to reach a final validation loss of 0.39 and validation accuracy of 86.7. Next, Cameron will tell you about our Inceptionnet model.
Cameron here. Our second model used an inception net for the base. So the most unique aspect of this architecture is the use of inception blocks, which apply convolutional kernels of varying shape and sizes to the same input tensor and concatenate the outputs of each kernel. In doing so, InceptionNet is able to extract features of different sizes from the same input without creating a model that is too large and prone to overfitting. This lends the model more discriminative capability without making the training procedure too cumbersome. And here you can see an example inception block where the kernels of varying sizes and the results that the model achieve on its own during training. As you can see, validation loss was pretty volatile for the first few epochs, but eventually stabilized as training progressed. Now I'm going to turn over the mic to Jillian so she can talk about Efficientnet.
Jillian here. So the final transfer model we created used Efficientnet as the base. Efficientnet is an umbrella under which there's a family of models from Efficientnet B0 to Efficientnet B7. When we think about convolutional neural networks, we have 3 scaling dimensions we can adjust: depth, width, and resolution. If you look at figure 7, we can see the architectures of each. The thing is, if we scale each individually, we often reach a threshold where improvement plateaus or even starts to decrease sometimes. For example, consider depth. We can scale depth by adding layers, but if we continue to add layers, we eventually get to a point where adding more layers doesn't improve the model. For example, ResNet 1000 has similar accuracy to ResNet 101. The idea behind Efficientnet models are to improve accuracy and efficiency by uniformly scaling the network's depth, width, and resolution. To do this, we use compound scaling denoted by phi. In the chart below, we see how depth, width, and resolution are scaled by phi. After training our model with a batch size of 16, 100 epochs, and a starting learning rate of 0.001, we have a model that hits a peak validation loss of 0.38 and a validation accuracy of 0.877 at 59 epochs. Now we want to discuss further interpretations of our model, so I'll pass it on to Cameron.
Cameron here. So after training, we examined the behaviors of each model with respect to individual classification behaviors, where they succeeded, where they failed, and how we may be able to combine them to make an even more accurate model. To visually understand which images the models were struggling with, we took the 15 images from the training set that achieved the worst loss values for each model. However, there wasn't much of a trend for any of the models, so this didn't prove to be as helpful as we hoped. Nonetheless, it was interesting to see where our model's weak spots were. Then we created confusion matrices for each model to get a more aggregate sense of where the models were misclassifying. This also created a correlation matrix of model predictions to get a sense of how different the models were in their classification behavior. Since correlations between model predictions weren't too large, but accuracy among individual models was all high, we chose to ensemble the models together to create one supermodel. And with that, I'm going to turn it over to Chris to discuss what exactly ensembling means.
All right, Chris again. Ensembling is simply the process of combining multiple models' predictions in a way that utilizes all of their different strengths. There are many different ways of exactly implementing this kind of strategy, the 2 most common of which being majority voting across your group of models and combining softmax outputs in a way that effectively averages their predicted class probabilities. We decided to use the second approach here because we thought that it made more sense given that we would only be able to take the majority vote over 3 models. To do this, we built a single composite model that gives the same input to all 3 of our transfer learning models, and then adds their 3 softmax outputs, each being a 5-dimensional vector of class probabilities, and formulates our final prediction based on the class corresponding to the maximum entry in that sum. Now, Cameron and Jillian will lead you through some of our reflections on the project overall.
Cameron here. So if we had more time, there's a couple things we would have liked to do. One was to further investigate the previously mentioned improvement attempts. For example, we would have liked to apply a small learning rate to the base layers and a higher learning rate to the head layers. We would have also liked to examine the Efficientnet family of networks more closely, like Jillian had mentioned. While Efficientnet B0 was pretty successful, we would have liked to train other variations with more hyperparameter variation and for longer training times. Another approach we were interested in but didn't have time to implement was to consider the use of classical methods like k-nearest neighbors to draw the final decision boundaries for a network in order to replace the linear decision boundaries of the softmax output with a richer nonlinear transformation. And with that, I'm going to hand it over to Jillian so she can talk about the takeaways and what we learned.
Great, Jillian here. So we really enjoyed this project and learned a lot about image classification models, working as a team, and Kaggle competitions. Before we sign off, we want to highlight some of the tools and concepts we discovered. So this project proves something that many of us have learned or already experienced, that often enough, a lot of our time is going to be allocated to adjusting code, fixing bugs, and implementing our pipeline. Next, we also discovered this new tool called weights and biases. This tool is a great way to monitor models while they were in training, store different training performances, and easily create adjustable graphs to display performance as seen in the blog post above. This project also introduced us to TF record and the benefits of using it. Finally, our most notable conceptual insight was the benefit of ensembling, which allowed us to combine our models and achieve a high accuracy. That is the end of our project. Thank you so much for listening. We hope you enjoyed our project, and if you have any questions, feel free to check out our post or write us a message in the comment section below.